Okay, so far we've learned about the Bohr model, our basic subatomic particles, neutrons, protons, electrons, and where you would find these and things like that. And it's all been two-dimensional. And the Bohr model is excellent for so many different things. It's why we bother to learn it. But it does have some limitation. First of all, atoms aren't two-dimensional, they're three-dimensional. Secondly, electrons don't always stay in a perfect little circle like a planet revolving around the sun. It's a little bit more complicated, and the proportions are a little different, as we saw last time in realizing that most of the atom is actually empty space. So there's not this significant of a difference. You wouldn't have an electron this close to the nucleus, and such as that. So let's take a look at what we do know. So in the last video, we learned about this electron cloud, and the fact that they don't follow a perfect pattern, but they make up this misty cloud-looking thing, which is a potential of any place that the electron could be around the nucleus. Now what we need to understand is within that cloud, we actually have all of these much smaller, odd-looking shaped orbitals. These are actually electron microscope images, I believe. And it's based off the work of a whole bunch of people, including Heisenberg, Bohr, Schrödinger, Planck, and Einstein. Schrödinger, you might remember for Schrödinger's cat, and he has the idea of a cat in a box. Well, that comes from his study of the electron, because it's basically, as soon as we were to grab one, it would no longer be in its proper place. It would be in our position. And so we would mess up or interfere with it by actually grabbing it. So instead, he needed a prediction of where that electron could possibly be located at any given time. And that's what a lot of these orbitals are. They're where electrons can be found at any given time. So on that same line, the quantum mechanical model, it tells us the probability of where we would find an electron. And no, it can look a little bit different from what you would expect. This is actually one of our orbitals here. But know that it's not wrong what we did with Bohr stuff, because notice how there's still nodes in between. That's because it's still based on energy levels to where it might be, how far out it might be. It's not a perfect line that they sit on. There's a much more dense cloud in that area. And it's not always spherical. Sometimes it is very odd shapes like this where they could be found. But it would get bigger the higher energy level you go out. Those energy levels are the exact same thing we were looking at before with the rows on the periodic table, or periods as we call them, right? So when we said that, electron would be found in this shell or this shell of the atom, we weren't lying. That's still the exact same thing in the Bohr model. It's just in a three-dimensional type image, and it might not be in a perfect circle. We're going to designate those as N1, N2, N3, N4, all the way to N7, because that's how many rows we have on the periodic table. With each energy level, electrons will occupy sub-levels, though. So the energy level is how far out, but depending on where it is, it might be in a different type of suborbital. And we need to learn those. Okay, so let's take a look at a quick overview of the 4 sublevels we have. So there's 4 types of sublevels, but each one might have different amounts of those sublevel orbitals in them, okay? So the first up is a spherical, is the S sublevel. It's most common, and it only has one possible orbital for that spherical thing. Next is P sublevel. It's dumbbell shaped, and it can have 3 possible orientations. And we'll look at all these in a little bit more depth in a minute. D sublevel, kind of clover shaped, kind of not, but that's the closest shape I can think of. And it's 5 orbitals, 5 different possibilities there. And then F sublevel, it's just really, really complex. There's no real shape in nature that you can think of that describes it very well. But it has 7 different possible orbitals. Now, the reason that I'm telling you about the different orbitals, because electrons are kind of funny things. We talked about electron pairs a while back, and the electron pairs comes from these smaller orbitals, because each orbital can only hold 2 electrons. and that has to do mostly to the electron's spin. They spin in opposite directions. We designate it as an up or a down arrow, but it's a true spin. It gives a lot of stability and balance to our actual elements, and each orbital, so the s sublevel, can only ever hold 2 electrons. Since the p level has 3 orbitals, it can hold 6 because you can put 2 electrons in each orbital. And so 10 electrons in this one and 14 in that one. It's a good way to remember it. These links that you see, don't worry, I'll put that on another page so that you can do further research yourself. It just goes into more detail. So let's look real quick at each one individually. This is our s orbital. Remember that it is spherical, and so you can see there's a little half circle. It's like cut in half. But notice this would be 1s, 1 energy level. That's N1, by the way. And then the second one would be surrounding it, and the third would be surrounding it. So notice there are the nodes, so there's that empty space in between where you probably would not find an electron because it doesn't have the proper energy. The energy level does get larger as you move out. And they're all spherical, but they're wrapped around one another. So you can have 1s, 2s, and 3s. And this is the orbital, and that orbital can only hold 2 electrons max for each one of these. Next, we have our p sublevel. Like I said, looks a bit like a dumbbell, and it's easiest to remember each one of the axes is the way that you can get 3 different configurations of it. So if you think about an X, a Y, a Z, that's a 3-dimensional space and everything. That's how you would get these orbitals. Each one can hold 2 for a max of 6. And it does look a little bit different. This is a little bit more, but this shows you a little bit. So this would be N1, N2. See how it gets bigger and further out. N3, it's now 3 of them. N4, it's 4 of them stacked. N5, and so on. Next up, we have our d orbital with its 5 different configurations. We say it looks like a clover, mostly because of these 4. I still think this one looks like a pacifier, a double-sided pacifier of some sort. But again, it's the exact same thing. Each one of these can only hold 2 electrons, spinning in different directions. But as they get bigger, they just go further out, and so you get a larger and larger combination of them. And lastly, we have our f orbital. And look, yes, it is super complex, but this is your 7 different possibilities that you can get for that f orbital. Again, 2 electrons apiece spinning in different directions, so a grand total of 14 electrons. I don't really know what to call this look. That one almost looks like a pacifier, but then it has these, I don't know, maybe a jack. It's hard to say. So this gives us a great breakdown of each orbital and the energy level that it would be. That first energy level is just going to have an S. By energy level 2, you can have S and the first P. By the third, S, P, and D. And by the fourth, S, P, D, and F. But then notice it kind of breaks down because some of these become more theoretical than anything else. Doesn't mean that they don't exist. It means that we don't have any electrons that have actually started to fill them out. Although we do a little bit here, I think, now. And so it's just this idea that you can put electrons in different suborbitals. And see, this is actually a notation you won't have to learn this class, but we will have to learn a different kind. Great overview. And I would make sure we copy this down, much more simplistic. Energy level N1, that's row 1. You only have 1 sublevel. It's your s orbital, which can only hold 2 electrons. N2, 2 sublevels, an s and a p, and that's going to give us a grand total of 8 electrons, 6 for the p, 2 for the s. And you can actually see this is how we came up with the maximum amount of electrons that each period on the periodic table can hold. 2, 8, 18, and then we go all the way up to 32. So it's just an interesting bit, and I think just the concept this time is enough for now. Next time we'll look on actually writing this configuration.